Welcome to the Weekly Squeak, your weekly geeky squeak with me, Chris Chinchilla, back for another week. I have an interview this week with Peter Suma of Nengo, talking about their quite fascinating AI model training brain simulation project. I haven't had a chance to get hands-on with it myself, but as you'll hear from the interview, it is quite fascinating, and I hope you find it interesting too. I hope you're all safe and sane out there. I am going to not explicitly mention again what I'm talking about, but I'm sure you know, and I have a few links that allude to the situation, but I want to keep this a free zone where you can enjoy geeky wonder without having to worry too much. So, all that said, let's get straight to my links for the week. Firstly, an article from Torben Frier on a website called Sifted. It's actually someone we do know, called controversially, Berlin is crap and no one is talking about it. This is directly in reference to the startup scene, in case you're wondering if it's more general. And Torben is fairly scathing of situations that make Berlin not that great for startups, as much as people may think. Things like Berlin is great to live, but mostly only for employees. Or not that, obviously, employers are kind of people too, but, kind of looking at it from that perspective, that for employees, it's often better than their employers, shall we say, because of rights and things like that, workers' rights, etc., etc. One of the main negatives he cites is the limited investment pool, and albeit then a fairly conservative investment pool at that. He also mentions there is a fairly limited pool of talent for senior hires, and I know many companies who have witnessed this and often have to go fairly far flung to find senior people who are actually worthwhile hiring for roles that need any sort of form of experience. For junior, it's mostly fine, and juniors can take you some time. And of course, juniors can become seniors is another point to make here, but it's an interesting point that I often hear, and often seniors are attracted elsewhere where they can get better wages or higher wages. Better and higher are not necessarily the same thing, but that is maybe best saved for a discussion another time. And then finally, the point that everyone always expects. German bureaucracy is a pain, especially a pain for people running businesses. Mostly for employees is better, although still a bit of a pain. Now, interestingly in this article, and you can certainly find the links in the newsletter version of this podcast, there's a lot of fairly negative comments on this article, mostly relating to the fact that Torben didn't work for a particularly large company, and he doesn't really know what he's talking about, that he couldn't attract people because he wasn't attractive to them, etc., etc. I'll let you make your own mind up. They always say don't read the comments, but some of the comments may be valid, some I don't think are, some I don't think are fair, but still, if you have an opinion on Berlin being good for tech or not, have a read and let me know your thoughts at christiangela.com/contact. Next, this is an article from ZDNet, from Mary J. Foley, but actually widely reported. Why? Well, widely reported, but kind of quietly snuck under the radar, I guess, in a lot of other news. And this is always a point that people will make sometimes when the news is full of other things, other stories sort of vanish into the unknown. And this is the story of GitHub/Microsoft buying NPM. NPM, the package manager for JavaScript, very widely used, but I guess they probably were struggling financially. So for them, this was a very obvious pairing. This does start to make some people worry that there's too many eggs in one basket, too many eggs in one corporate basket, too many developer tools owned by one company, albeit a company that is largely now in developers' favor. But still, this is somewhat concerning. Also somewhat concerning that very few people seem to have much of an opinion on it, which is also strange in itself. But in terms of integration options, this will probably get better and better. I'm wondering if GitHub and NPM will just sort of merge into some kind of odd cohesive whole. We shall see. But one to watch and one to watch out for, maybe looking further forward. Next, an article from Charles R. Martin on the overflow. An interesting historical look into the origins of the Hello World demo application that is often there in many, many, many code tutorials, where it came from, and maybe a more modern version of it. has Hello World kind of run its course for developers trying to learn something useful? And he proposes a couple of pointers for a modern Hello World. This being things like actually organizing code into folders and maybe separate files to introduce the concepts of things like dependencies. He also mentions adding version control by default, which is an interesting one, actually, and teaching people how to use version control straight from their Hello World experience. He also mentions then maybe introducing tooling around coding, IDEs and editors and setting them up, etc. He also mentions build processes. I would start to wonder if this gets a little complex for people getting started. Some of the others maybe. A build process, or as he clarifies here, a repeatable build process is maybe getting a little complex. I mean, running is something that is definitely done in most Hello World applications. And then as a virtue of that, then it is built. But I wonder if that's getting a little complex. And then he says, then start coding. So I wonder if this is maybe too much for many people getting started. I'm not sure. It might be maybe a Hello World and then a kind of Hello World recommending next steps, maybe something like that. I'd actually like to hear your opinions on this, and maybe I should get him on as an interview subject actually to go a bit deeper. Do you think Hello World is enough? What else would you add to a modern Hello World application to make it somewhat realistic in the kind of modern world of programming? Next, an article from Seth Kenton on opensource.com. 10 open source tools for working from home, wherever you might be working from home. Some of these I definitely knew of already. Things like Jitsi, although I didn't actually realize if Jitsi is open source. I thought it was owned by Atlassian, but maybe I'm wrong. Some you definitely know, things I say like Jitsi, Nextcloud, Etherpad, Ethersheets, but then some others here that you may or may not know, and some that I did not know and I will definitely find very useful. Things like Joplin, a sort of Evernote replacement, which I have been looking at myself recently, but also a collaborative drawing application here called Drawpile, which I would really have been looking for and did not come across. So I look forward to trying that very, very soon, actually, and seeing how well it works. He also mentioned some Kanban, i.e. sort of Trello replacement tools as well. Riot for chat, which I have used, actually, and mostly works fairly well. And, of course, LibreOffice, Linux, some classics like that. Some of these actually, took me by surprise. I had not come across before and look surprisingly good. Some, I'm not 100% sure how fully open source they are. But, if you are now working remotely but would like to stick down the open source path, take a look, try some of these and see how you go with them. Next, an article on Mel magazine from Brian Van Hooker on an oral history of how the movie War Games inspired Ronald Reagan's cybersecurity policies. I won't go into masses of detail to not sort of give away the story here, but if you know War Games, the movie, when a hacker manages to accidentally kind of hack into what he thinks is a game, but is actually the kind of weapons control system in 1980s America, and inadvertently starts a war. And Ronald Reagan, being a film buff and an ex-actor, watched this and then came in the next day and asked advisors, is this possible? And a lot of his advisors actually quite interestingly came back with, yeah, actually could be. And should we do something about this? And they did. So bizarrely, fiction did influence fact in this strange case. So have a read through. I would be interested to know if any of you older hackers out there remember some of these problems and could corroborate whether these facts may be true or not, and if it was actually possible, ignoring all the drama and storytelling, is it actually possible to accomplish this? Or is the article wrong as well? Please do let me know. Comments on this article and any others at christianschiller.com/contact. Next, an article from the National Geographic, not a publication I often cite, called Dead Sea Scrolls at the Museum of the Bible Are All Forgeries. This sparked my interest, not just because of history, but before we were all forced to stay at home. I actually just got back from Israel and we went to the Dead Sea and we were told the stories of the Dead Scrolls and were shown where many of them came from. So I thought, oh no, all those are forgeries. No, that is not true. This is just a specific collection at this specific museum that have been shown to be forgeries, which is a great shame, especially as I think, judging by the name of the museum, this is probably something that's quite important to them. And it details how something like this might be found to be a forgery, why they indeed even checked in the first place, and what this could mean for the rest of the scrolls. Actually, in this case, most of the others have been shown not to be forgeries, so it's just this batch. But actually, the story we heard whilst we were in Israel was that the Dead Sea Scrolls were quite a lucrative affair. So creating forgeries, passing them around, selling them to collectors and museums was quite a common thing to do, mostly because they were nomadic tribes who found them. So it was a great source of revenue for them. So there's highly likely to be several sets of forgeries out there. And I'm pretty sure I remember hearing that there have been previously found forgeries. So this is not necessarily the first or indeed the last. If you like ancient with a modern twist detective stories, then have a read. And finally, we've been playing a lot of games online the past couple of weeks. I might actually even do a roundup of options for that in the future, although I kind of feel like everyone that has been done by a lot of people already, but maybe I have some particular points I can bring, maybe even looking at it from a designer's perspective instead, I'm not sure. But these are board games and roleplay games for two people to not necessarily play remotely, but play together, a family, a couple, etc. And there's some great ones here, some that I definitely knew, some that I did not know. Some I look forward to trying, especially some of the options in the roleplay section, which are more the kind of building together storytelling roleplays, which I actually really, really like the idea of, and I think I could encourage my significant other to join in. So I look forward to trying some of those. If you are looking for some inspiration yourselves, get a hold of copies whilst you still can. Take a look at this post on Gizmodo from Beth Elderkin, and enjoy playing. Let me know your experiences of playing some of these games. Now my interview with Peter Sumner from Nengo. Now this was a very interesting interview because I have never interviewed someone, and I mean this in the best possible way, Peter, if you are listening, that talked so much. I did not have to ask very many questions, and he gave some very, very thorough answers. So you don't actually hear very much from me in this interview. He answered most of the questions I would have asked very, very well. And it was quite interesting just sitting there and listening. So yes, I do reiterate it again. I do not mean that in a bad way. I mean that in a good way. I enjoyed the interview. I found it quite fascinating. I really look forward to getting my hands on in the article that will accompany this interview in the future with the platform myself and trying it. But in the meantime, enjoy.
Oh, okay. All right. Fair enough. Well, look, thanks for the interest in the company. What do we do? So effectively, we do two things. Right now, what we do is optimize AI. And we use techniques that were discovered by my partner. So I'm the co-CEO on the business side. The technical brains of the organization is Dr. Chris Eliasmith. And Chris is the head of the Center for Theoretical Neuroscience at the University of Waterloo. And so he's an electrical engineer that got a fascination with, hey, how do brains work? And I think it's based around electrical circuits. And so years ago, he did a PhD in neuroscience psychology and then met up with a physicist, and they got to thinking about how could you mathematically describe how a brain takes information from the outside world, turns it into representations somehow in the electrical activity in brain circuits, and then transforms that through learning and memories. And then how do the dynamics of how neurons work be controlled in the brain? If they're all spiking away, how come you don't just get garbage as opposed to useful computation and high level behaviors? And so the structure of the brain, the structure of circuits. And so we put together a set of mathematics that basically you could create a mathematical model of how groups of neurons work to do that process, take information, build representations, learn, and as well control their activities to be able to recall that information and make behavior. So all of that is basically the foundation of the company. That math got turned into a piece of software called Nengo. And so Nengo is like a compiler that you basically can visually lay out circuits of neurons. And it was originally absolutely only used for brain research for 15 years or so, to build simulations of circuits that were found in the brain. And so his lab, he eventually did his PhD and went to Waterloo, started a lab. The lab was basically in the business of saying, okay, well, if this is sort of correct, let's go build models of brain circuits. Let's go to papers where neuroscientists had speculated on how the circuitry of the neurons found, how they connect, how they behave, their activities, that would produce things like how you smell, how you see, how you process sensory information, how working memory works, how vision might work, etc. And there's been lots of papers, both from the neuroscience community and the AI community over the years, speculating on these circuits. And so Nengo was used to very quickly develop models of these circuits and then run them and then compare them to the real data coming out of when people put probes into worms and other animals in the lab. They'll publish their data. Well, here's the situation the animal was in. Here's the stimulus we applied. Here's what we saw as the spiking behavior of the neurons. And so when you compare that to an artificial model of that same circuit, if your circuit design is what's going on in the real brain, in theory, if the two match, you get some pretty good evidence that your circuit diagram is probably what's going on in the biology. And as maybe far-fetched as that might seem, it worked way beyond, I think, anybody's expectations for many years. And the brain is extremely complicated and has many, many, many different circuits and many different computational systems or algorithms that it's computing at different places. But they were able to explain a lot of circuits found in the brain. Now, when we say that, we're explaining small parts of the brain, one by one. The brain is 100 billion neurons, trillions of connections, and as I said, uses many algorithms, not just one. So the work progressed. Then in about, so this is sort of in the 2000s, coming up into 2011, I ran into Chris and I was looking for somebody who was working on full loop AI, something that sort of said, let's take what we knew about brain circuits and build higher order copies of it, because sort of simple AI backpropagation is powerful, but it certainly doesn't seem to explain how intelligence arises. So anyway, the process became, or the events became, that in about 2015, Intel approached us as we were trying to commercialize Nengo, not for brain circuits anymore, but to build better AI, more intelligent AI. How do you integrate a vision system with a working memory system, with a decisional system, with a motor system? How could you make a smarter robot by trying to copy how the brain does that, and using Nengo to build each of those circuits and then integrate them? And effectively, IBM had built a chip. All of this relies upon neurons being computed with. IBM had built a chip called True North, and Intel saw that. And the bigger backdrop of brain chips, why would anybody want to build a chip that has a sheet of neurons right on the hardware? And the idea was that, and still is, that neuromorphic chips, in theory, we're getting Moore's law is breaking down. You can't just make the transistors smaller to get more throughput. So maybe if you do what brains do, looking at a brain, it sort of says, well, each neuron's actually kind of slow, like way slower than most of the computer chips we work with. But there's billions of them, and they all compute at exactly the same time, like in parallel, but not necessarily synchronized. They're quite independent. They do use certain mechanisms for synchrony, but effectively all the pieces of the brain are always on and working together at the same time. And so the thought was, if you parallelize the problem massively and got rid of the clock that a von Neumann chip works on, there's a clock tick, and every part of the system works to that tick. And GPUs have multiple clocks, but they still have clocks. So was there something special about going massively parallel, massively asynchronous, and removing the clock, and then using this idea of a neuron structure to compute with? And if we did that right on the hardware, would that make really, really fast AI? And by the way, is there something special and secret about this, that we're going to get a big advance algorithmically if we do these things? Like, is the future of AI in an architecture that looks like a brain in this way? And so 2015 comes around, and we started the company sort of 2014, and we've been doing some research contract work for places like DARPA in the States. And Intel showed up and called us down to a meeting and said, look, we're going to build this chip. We are doing it Intel Labs as an exploratory research project. And IBM's got their True North, and we're going to build a chip like this, except we're going to do it way better. And they did, and their chip is way better. But you guys, so we get a chip. Effectively, once they build a chip, you look at this chip, it's got 128,000 neurons. They're each independent. If you stimulate any of them, they start spiking. You've got to figure out how to connect them. You've got to figure out how to make them learn things. You've got to figure out how to control their dynamics so that once you connect them and send one of them spiking with an input in response to some stimulus, visual, sound, whatever, and you're trying to make vision recognition or image recognition, well, if they're all connected, they'll just all spike away. And then the whole thing goes to what we call saturation, and the output is basically garbage. Like, it's just a whole bunch of random spikes. So how do you connect? How do you control a symphony, something you need to have a perfect orchestrated symphony flow through? There's no clock, and you need them all to work together. Well, it comes down to setting how they connect and the timings of all the signals and the kinds of the ways in which, trying to keep it simple, the ways in which each of the neurons processes its input. And that's basically a set of millions of parameters that the chip needs to be given. It's one thing to produce a chip, but it's basically a blank slate. And you need to know how to do that. Well, that's exactly the same problem that Chris Eliasmus solved when he created the mathematics called the Neural Engineering Framework model and the software called Nengo. And Intel realized that early on. They talked to all the labs in the world, and for about 8 months, they came back and said, "You guys are the best there is, if not the only solution to this problem. So let's work together." And we did from 2015, 16 till today, making Nengo be the visual compiler for the research chip Weehee. And in addition to which, we've done this same thing with the brain drop chip at Stanford, the Spinnaker chip in Germany, and an increasing number of, we also support CPUs and GPUs. So today you can build an AI model visually, and you can make it do everything from deep learning to reinforcement learning to liquid computing, all manner of neural modeling. And you can have that model at the press of a button run on your CPU, on your GPU, or if you have one of these, access to one of these new research chips, a neuromorphic chip. And in the process of doing that, commercially speaking today, what that means is if and when neuromorphic chips are released, which looks to be around 2021 for the Spinnaker chip, and there are a couple of others in the works as well. Intel, we don't know. It's a research project out of Intel Labs. But when it releases, you'll have a choice of programming the chip directly, very low level, or you can download Nengo and program it visually. And also something no one else has, you can actually debug visually, which is extremely useful if you actually do this. So Nengo is available at nengo.ai. So it's a compiler for AI, dynamic temporal AI models. And what I mean by that is this kind of AI, these kinds of systems do the best job on the same kinds of problems that brains solve, which is flowing or temporal AI. So if you're processing a set of visual input from a camera, or speech, or sound, or sensor data, or control data in an autonomous car, all of these things are characterized by data flowing in a constant stream, which is a temporal stream. So what that means is, if you look at a video, the data you get at any instant is related, it's dependent upon the data that came before it and the data that flows after it. It's not like processing a stack of unrelated images where each image is a brand new thing. It's not related. If it's related to the thing in front or back of it, it was by chance, not because it's a consistent stream of sensor data. So these kinds of AIs, all these little neurons, each neuron is stateful. It holds a certain amount of state over time. The way you connect them respects the idea of state. And the algorithms they're most efficient at processing are those that are continuous in time. So like your retina, you may know that when you look out at the world, you only have about 1 million fibers coming out of the back of your eye. And so you've got pretty low resolution, if you want to think of it that way. But at the end of the day, what's going on there is you're processing the change in the environment, the visual environment, not constantly reprocessing all the background. And that's efficient. And evolution discovered that. And so we use that. We call that temporal sparsity. So our systems are better and more efficient at processing constantly flowing temporal data streams because these neural systems learn and respect and take advantage of the fact that the signal is correlated in time. It has a relationship. So it ignores duplication of signal and it focuses its computing efforts on the things that change, making it more sensitive to change, more accurate in time, and less energy is used to process a constant flowing video by not reprocessing the background information, for example, over and over and over again. Similar to how TV sets work. They download the delta of the frames, not the whole frame every time, right? So effectively now Nengo is this brain circuit modeler which solve the same problem that is present in programming neuromorphic chips. As a consequence of that, and because Nengo supports CPUs and GPUs, et cetera, you can put one model in and run it on all these kinds of chips, existing chips and ones that are still not yet released. And because it does a better job of processing temporal AI, all these sensor, video, et cetera, signals, you end up with a visual platform to build AI models, build them once, run them on all kinds of hardware, and have them, if they're processing temporal flows, have them be way more efficient than traditional AI. So we use, in the parlance of AI programmers, we do use weight sparsity. We do all kinds of mechanisms to compress our networks like everybody else does. But then in addition to which, we compress or sparsify the temporal processing as well. Secondly, the visual, the performance advantages, and then lastly, these platforms support deep learning, reinforcement learning, liquid computing, all of that at the same time. So you can build these multiple or full loop type AI systems easier. So for example, we build advanced drone brains that have the visual system looking for things like defects in infrastructure, connected to an adaptive motor control system, connected to an adaptive path planning system, and the three of those subsystems run together put onto test or research pre-release neuromorphic chips. They're going to fly the drone way longer than if you tried to do that the existing way, which is with like an edge GPU or something. It just sucks way too much power to even do just the visual task. So you're not only compressing, the benefits of compression aren't just the energy, it shows up in the actual flow through the system because it does less work to achieve higher order behavior. So you get more adaptive and responsive autonomous intelligence, and it allows the autonomous systems to function much longer. So the net of all this is, where do you use this stuff? Basically, if you have any form of constantly flowing data, you want to push it through an AI network or multiple networks to produce some categorization, classification, control loop, etc. And typically those situations are found, and you care about power and you care about response time. Typically those situations are found in devices that operate in the real world, in a behavioral loop locked with the world. So autonomous cars, drones, robots, sensors, etc. And that's where we're finding our niche. Beyond that, the last thing is all of these systems from the ground up, because they support state right down to each neuron, unlike what you'll find in deep learning, traditional deep learning. These systems also lend themselves to basically temporal based learning. So they do a very good job of learning at the edge. So the other big deployment area is taking Nengo, building models with it, converting them, frankly, from TensorFlow or from some other frameworks, and you basically then take that model and push it out across multiple hardwares. So it's a very good platform for IoT in the sense that you have lots of edge platforms hardware, but you want to have one model. When you deploy it, you want it to run, and potentially, depending on what you're doing, you want online updating and learning at the edge, which you back propagate to the central model. So we're working with some companies to integrate Nengo into their IoT backbone to give them the visual compile, the efficient at the edge, low power, and the multiple hardware, plus the online learning at the edge. And other than that, those are the uses of the products. We do an awful lot of research for corporations and military on AI algorithmics, because in studying the brain, it's really the case that you very quickly get pushed out of the idea of one network to do classification or categorization. You're immediately into an environment where you're trying to understand how it's the integration of the multiple networks, and it's dynamic and temporal integration. It's all flowing. It's all signals thinking, not static thinking that you have in traditional AI. And it's all stateful, both at the neuron level and the network level. And so taking inspiration from that, you immediately find it quite natural to look at integrating vision plus adaptive control plus flight path planning in a flowing dynamic way. And that also we do work, for example, in robotic scene understanding. We do work in lifelong learning, which is making AI less brittle, taking ideas from the the parts of the brain that are responsible for why the cortex isn't as brittle as traditional AI. And we do an awful lot of work also with some security agencies around something called dynamic computing. And those research projects are advancing our algorithmic understanding. And then we use that advanced understanding to put back into Nengo and into the applications we develop, whether it's for a phone company making a super, super low power edge speech system, about 3 times more efficient than state of the art using our techniques. The adaptive drone projects, and as well, we're working with one project that's public is we're working with BMW. They've been talking about it to dramatically reduce. We reduced a vision test system. We reduced its power usage by 53 times. So instead of, a test car will have 30 to 50%, an autonomous car will have that much of its total power budget going to compute. And so for the AI workloads in there, the initial tests suggest we can cut, that AI workload down to 2% of its original workload. That means dramatically different top line sticker energy efficiency in the showroom in future with neuromorphic chips and Nengo powering the visual system, et cetera. So I think I'll stop there. Tools, applications, and you're recording it. So you told me you're recording it. So I'm going to save you the whole time. Tools, applications, and research for military.
Okay.
And
that was an extremely comprehensive intro.
Yeah. Well, I'm sorry. I just the problem with this is that it's a whole new platform, and you'll find when you play that back and probably type it up, the true understanding comes from seeing everything, both what it is, the layers of it, chip to software to application to features to benefits, and being able to run up and down that and see it differently, similar to how, you've got the paradigm today of deep learning and GPUs, but it's got flaws. This is better in some ways, not in every way, but certainly in a lot of ways. So I wanted to get that across.
Yeah. I think the one thing that I had in the back of my mind throughout that explanation was, so I'm looking on the Nengo site and I see kind of, you're pushing it as something that's easy for people to get started with, but I'm just trying to understand, how would someone use this? Do I have to have access to one of these particular chips, or can I run an emulated version, albeit with low performance? Like, can anyone try an Nengo for a particular use case, or do you have to have access to something special?
No, you absolutely don't. So, look, it is, if you're trying to come into this world, Nengo makes it easy in the sense that it's visual. What the website doesn't say is, it is, there's a getting started page, and we take you step by step and encourage, like all development platforms, we encourage you to immediately go and download examples instead of coding from, blank screen stares at you, right? So that's why the getting started flow is jump into an example quickly, because it just makes a lot more sense by teaching that way. And that's the same for, TensorFlow or any other platform. The one thing that is challenging and is that everything in neuromorphics is a signal. So the kinds of backgrounds that tend to understand this easier are people that come from signal processing, DSP or something like that, or any form of neuroscience, or whereas traditional old programmers like me, it took a while, and I won't understate that. It can be, for certain backgrounds, difficult. You have to let go of the idea of this linear thinking that you find in traditional von Neumann computing. Step 1, clock 2, event. These things, operations are done, then the clock moves forward. Here it's like, I created, all these multiple neural ensembles and signals are flowing everywhere. Oh my God, what do I do? How do I control this? And the neural engineering framework will definitely help you there, but you definitely have to stick close to the examples till you kind of grok it. So that said, there is a bit of so step 1 of what you were addressing. Yes, there's a bit of a learning curve. It's a paradigm adjustment, but once you're through the looking glass, you understand the benefit of it. And you start to build systems like dynamic control systems. One of the examples is like the brain of a Pac-Man creature. And if you stand back from that, it's like 25 lines of code, and you go, wow, this thing's got pretty cool dynamic control systems, avoiding predators, seeking food, all of that sort of thing. And you're stepping back and going, that's a lot of functionality for a small amount of code. And that's one of the benefits. Moving on to your second question, what do you have to, where do you start with this? The whole idea of Nengo is that you can build a model and just run it on your CPU. You just download Nengo and it'll pick up and use your CPU. If you have a GPU, you can build the exact same model and it'll run a little bit faster on your GPU. The just cautionary tale there, but an important instructive point around the general future of AI networks. If your model is a highly recurrent network, as we find in the brain, so lots and lots of signals. The brains are based around processing state. So one of the things you want to do if you're processing state, of course, is you want to send signals feedback. You want to you classify an image, you want to send the classification from a few milliseconds ago back to the beginning of the loop, because that may inform you as to what you're looking at, because brains are used to living in a world of continuous flow, like I said earlier, signals that are related. So they care about, it's not feed forward flow, it's massively recurrent flow. Well, if you have massively recurrent flow, GPUs don't do that well with that compared to often. Sometimes you'll find networks run faster on the CPU. But regardless of what you want to use it for, you can easily test this, and then you can build the model once and then run it on the CPU, and literally click an option in the UI and run it on your GPU. If you have a neuromorphic, you can run it on that, but you can also tell Nengo to run an emulation of the Intel Loihi research chip, for example. And it will use your CPU or your GPU, but it will emulate that Loihi chip. And that's used to basically understand for people heading to deploy or research with the Intel chip, for example, or the Spinnaker chip, same thing. It gives you an idea of what you're going to see performance-wise, and in emulated time, it'll show you how that's going to go. But in general, no, you don't need to have those chips. That's why we built the software emulator for people. If you do have one of those chips, and if you're running a certain, especially heavily recurrent or temporal network, you're going to get big efficiency gains. So typically, we've published papers on arXiv for keyword spotting. We haven't published it, but the vision system work. There's adaptive control work. All of these things are showing 50 to 100, and Intel has test cases showing up to 1,000 or more times efficiency gains over GPUs. And it all comes from this idea of temporal sparsification, the massive parallelism, and the lack of the clock, the asynchronicity. And there's a couple other features about neural networks that lend for temporal tasks. They do a way better job than CPUs and GPUs. And so that's why we're trying to get ahead of the curve and get people into the space. But today, most people are using it with us mostly for the algorithmic benefits. It's a more visual, easier way to build a dynamic system for those drone brains, or to study robotic scene understanding, or more of a development platform advantage is what it brings today. And then the multi-hardware platform for the IoT devices. So you get algorithmic benefits of power in temporal sparsity without using a neuromorphic chip. You get more of them if you take that same model, flip the switch in Nengo, and say, go run it on my neuromorphic. If you have one, you'll get even bigger power benefits.
And also, to go alongside Nengo, I see you have the brain board, I think mostly for...
It's a test, yeah. So the brain board, it has to be clearly understood right off the bat. It's a small, all it is we only sell the bit stream. We probably shouldn't have named it brain board, but brain bit stream, but a lot of people don't know what a bit stream is. But if you buy a $150 odd, depending on where you are, or $200 FPGA development board from Altera or Xilinx, for $99, you can, or $79 academic, you can buy from us this file, this electronic file called a bitstream, and you download it and load it onto your FPGA board. And what it does is, FPGAs are field programmable gate arrays, are basically think of it like a tic-tac-toe board. It's like a mesh or grid paper. And at the intersection of each sort of vertical and horizontal wire, if you want to think of it this way, is a thing called a logic unit. And a logic unit is this programmable piece of hardware that you can make it into whatever you want. And so the idea with an FPGA is you can program it to be whatever circuit. It's like instead of getting an ASIC, a standard computer chip, which has a burned in set of gates and connectivity. And so you know what it does, a CPU, a vision processing chip, or whatever it is. An FPGA is like a generally programmable thing where you can emulate any hardware design that you want. So all we did was we took the resources of the FPGA and we turned them into, so that when you look down upon it after you load our bit stream, it reconfigures what our logic units into emulated neurons. And so the chip, once you program an FPGA with our bit stream, it looks to the computer that's programming it, as though it was a neuromorphic chip. It looks like as though it was a simple version of conceptually speaking only, like a Loihi or a Spinnaker, or one of the neuromorphic chips. And so the reason for doing that is that if you're running an AI model, now you're running it directly on the hardware in the FPGA, and you do get power reduction and throughput benefits. The one downside is we did that not as a production platform, but as a Raspberry Pi type of thing. So it only supports models with up to 30,000 neurons using a single ensemble. So it's useful to do things like keyword spotting or adaptive control or very small control problems. It's a test thing. It's mostly used in academic labs. So in Israel, it's taught in courses at some universities, and in Korea as well. There are some professors who basically have, 15 or 30 of these things in the labs. They bought the boards, they burned the bitstream on them, and they have Nengo, and they're trying to basically show the students, okay, so put the board into the mobile robot and then construct your small vision sensing algorithm or sound recognition or a little controller. And they're trying to give them a feel for what it means to have embedded neuromorphic networks in, and teach them the principles of neuromorphic time-based temporal computing. And that's what it's for. It's not big enough to do full vision, full speech, or any of the more interesting larger tasks. Those are, you need your CPU, GPU, or a neuromorphic chip.
Yeah, for sure. Okay. Final question then.
Yeah.
What's planned for the next 6 months or so?
For the next 6 months, we're focused mostly on. If I can extend that to a year,
yeah, for sure.
We expect the reason being is a big in the near term. We are integrating Nengo with IoT systems, cloud-based, large-scale IoT systems, to give people the benefit of, I want to deploy this temporal AI model, and I want to put it on multiple hardware, and I don't want to have to think about that, and I want it to run with less power. So that's works off CPU, GPU, microcontrollers, and we're extending Nengo's support for things like various forms of microcontrollers and various ARM chips and whatnot, so that we truly become a massively multi-platform. We have about 9 supported today, but we want more. And so it becomes a low-power temporal edge AI visual creation, compile, and deployment suite. And so if you've got sensors out in the field, et cetera, and you want to put speech recognition on all of them, and they can be from different manufacturers, et cetera, Nengo can take your TensorFlow or other design model, import it, spit it out the other end, and make it run on each of those platforms seamlessly for you, and it'll run lower power. So it becomes a piece of infrastructure and a tool for the developer to not have to write 10 versions of the software. That's the next, a key feature. And then a year from now, when the neuromorphic chips, the first ones we're hearing should roll out in 2021, then we're, if you want to program one of those, and you've got existing TensorFlow models, you want to convert them over to neuromorphics and run them to get the power benefit and embed them in devices and push the GPU out, because this is going to be 50 times or 100 times less power, then you need Nengo for that. At its core, it's temporal based. The TensorFlows of the world are not. There's going to be a huge, huge thing for them to support neuromorphic chips, and ours is visual day one. And the other thing I would caution people is it took 20 years to get that dynamics problem is a big problem, how you control those spiking neurons. Nengo does that better than anybody else. And we've seen lots of people in industry who are doing some of the first pre-release work with neuromorphic chips at major companies, try multiple different ways to do it, and come back to us and say, Nengo's the only one that's actually accurate and rock solid and actually works. And so I think people will figure out over time there's a huge amount of, it's the usual problem. There's a 1,000 or a million little things in there that were learned painfully over many, many years that Nengo does incredibly well. So that's supporting those developers as they want to take advantage as neuromorphic chips hit the world. That's a major theme. And then in the background, some of the really exciting stuff for us is these very advanced dynamical and autonomous computing systems that we're very lucky to have been selected to build for a number of our clients, whether it be on drone or in the abstract. We're working on some fundamental advances for AI. One last thing I'll point out is there's a lot going on. So you put a dozen PhDs with 20 years of experience each into a room, you got a lot of good stuff. There's a very exciting thing. This is actually very important. So we released a paper at NeurIPS this year, which fundamentally changes the state of the art around temporal signal learning. And this is we invented something called a Legendre memory unit. So Aaron Volker and Chris Eliasmith, it was Aaron Volker's thesis in one of the PhDs at Chris's lab. And Legendre memory unit was based off of the observation of how time cells in the brain, human brains, work. And basically, if you process speech or vision or pretty much anything time series related, not language processing, that's something that now they use transformers for, but for time series processing, so vision data, speech data, basically all the stuff I said, you today use something called a long short-term memory. So it's a neural network invented back in about 99. The earliest goes back to, I think, 93. And it processes flowing information and learns the patterns found in that. And then you can classify, oh, that's a word, that's this word, etc. The LMU replaces that, and it uses a set of mathematics called Legendre. And the Legendre characterization, I say, is you break down what's in the signal represent it using a series of curves that are more efficient, and they're actually modeled after how we think the brain does it. And you end up being able to learn a temporal signal, not just over like 1,000 time periods, of which an LSTM can do, but over 100,000 time periods. It's about 1 million times more powerful than the state of the art. And it's now, some of the first calls we got are from hedge funds, because now you can look at temporal data and have it learn patterns that humans can't see, but that extend over much, much longer periods of time. We have been able to produce speech recognition systems that are multiples of the efficiency of existing speech recognition. These aren't released yet. They're coming, though, and dramatically less power. And it does all of that while being 60% less in number of weights and size. So it's better and it's more accurate. It's more accurate. It models a larger time frame, and it's 60% more space efficient, and up to 50 times more power efficient. It's a big, big deal. The paper's up on archive. It's a patented algorithm, and we're basically now going into rebuilding speech and vision and other systems with it to capture those efficiencies.
And that was my interview with Peter Sumner. Hope you enjoyed that. Now, of course, not much travel happening. I am definitely trying some remote events. I am trying some of my first streaming and new podcast ideas. I just started doing some test recordings on a new storytelling podcast today, which was fun. I am doing a live stream on Thursday of this week that should, the podcast is out just in time. So to clarify, that is on the 26th at 1400 Central European time. I'll be live streaming me working on the new Ethereum wiki. So that could be interesting for some of you. And many more ideas to come soon on that front. I will hopefully be setting up some documentation kind of office hours soon as well. And if you feel like joining me for an online game or two, then let me know, and I'll try and add you to some channels when we do organize them. In the meantime, I will definitely be working on some more open source projects and things. Not necessarily anything to add right now, but there's definitely some things in progress that I will announce very soon in the next few weeks. So plenty happening, just all happening from the safety and sanctuary and yes, whatever other words I can't quite think of my home. I hope you've enjoyed this weekly squeak. Please do reach out to me if you have anything to say. Please rate, review, and share wherever you found this podcast. Very, very appreciated. And until next time, take care, stay safe, and thank you very much for listening.